One area of particular interest to many analysts, particularly in a manufacturing setting, is quality control. The various methodologies that have been developed in the past few decades have been given many names and acronyms, but a particular favorite is Six Sigma. At-Risk incorporates a number of common quality calculations with its collection of Six Sigma functions. You can see a list of them in the Six Sigma group under the Insert Function dropdown on the At-Risk ribbon. All of these. This video will explain how to use these functions and what they mean. The example shown here is used to illustrate Six Sigma functions. This is for a process that makes parts. The parameters in cells C10 and C11 indicate how the process is producing normally distributed parts. Mean 100, standard deviation 0.5. A typical part diameter is generated in cell C18 with a risk normal function. The parameters in cells C3 to C7, especially the first three, indicate how the company would like to produce parts. They would like the parts to have an average diameter of 100, and they consider any part beyond the LSL and USL specification limits to be defective. The 0,1 values in cell C19 to C21 indicate whether a typical part is within specification limits, below the LSL, or above the USL. And these three cells have been designated as at-risk output cells. The process with these particular parameters is called a 3 sigma process because the mean of the process is 3 standard deviations from each specification limit. These values are indicated in cells C14 and C15. You would expect a 3 sigma process to produce very few defective parts because a normally distributed value has a very small chance of being more than 3 standard deviations from its mean. As the Six Sigma functions will indicate, however, a 3 sigma process is not necessarily as good as you might think. The key to using the at-risk Six Sigma functions is to append the risk Six Sigma property function with arguments in cells C3 to C7 to the risk output function when the part diameter in cell C18 is designated as an at-risk output. To do this, you select cell C18, click the Add Output button, click its FX button, and click the Six Sigma tab, and then you fill the dialog box out as follows. You refer to all of these cells, Actually, the italics indicate that these values are cell references, as you just saw. And the value in cell C7 actually has no effect on any of the results shown in this video. Its role is quite limited. You then see that the risk output function in cell C18 includes the property function, risk Six Sigma, with those parameters. This addition of the property function has 2 consequences. First, when you run the simulation and then browse the part diameter cell, you will see the LSL, target, and USL superimposed on the graph. There they are. And I will move the sliders so that they are at the specification limits. As you can see, there are very few defectives. Keep in mind, however, that the given LSL, target, and USL are fixed. They are engineering specifications for this part. However, if the company's process mean is off target and/or its standard deviation is larger, the picture won't be nearly this nice. Here is an example where I will change the mean to 100.5 and the standard deviation to 0.75. Now I will rerun the simulation. Again, the sliders are positioned at the specification limits, and you can see that there are clearly a lot more defectives, most of them on the high end. Now I will set the mean and standard deviation back to their original values. And I will rerun the simulation again. Look at the summary statistics in column F. The first 5 are nothing new. They simply apply risk mean and risk STD DEV, standard deviation, to the output cells. But from row 11 down, you see the second consequence of the risk Six Sigma property function. It enables you to use the Six Sigma functions. Their names are spelled out in column E. Each takes an argument, which is the part diameter cell. There are other Six Sigma functions besides these, but the ones shown here are the most common. Probably the two most common measures of quality are the CP and Cpk indexes. The first of these, CP, is relevant for a process where the mean is on target, as it is here. It is scaled to be 1 for a 3 sigma process and 2 for a 6 sigma process. Larger values of CP are good and smaller values are bad. The Cpk index is for a process where the mean is nearer to one spec limit than to the other. In this case, there is a CP type value for each limit, shown in cells C13 and C14. And Cpk is the smaller of these. You will see an example shortly of such a process. The values in cells C16 to C18 are parts per million defective total, below the lower spec limit and above the upper spec limit. Similarly, the values in cells C19 to C21 are probabilities of defectives, either total, on the lower end, or on the higher end. Remember again that the numbers shown here are for a 3 sigma process, but even for this good a process, there are about 2,800 defective parts per million. This is why companies like Motorola decided that 3 sigma was not good enough. They strived for and achieved 6 sigma processes. But before seeing a 6 sigma process, change the mean to 100.5 so that it is closer to USL than to LSL and rerun the simulation. Now CP isn't relevant because the mean is off target. The relevant index is Cpk, which is based on the distance from the mean to USL, the closest spec limit. And it is well below 1. Now the bad parts, and there are a lot of them, are on the high side. There is one famous number you might have heard in quality control settings, 3.4 defectives per million parts. This number arises from 2 conditions. First, the process is assumed to be a 6 sigma process. However, the second condition is that the mean might have shifted off target by as much as 1.5 standard deviations. The idea is that a shift of this magnitude might take a while to recognize. At Risk lets you simulate such a shift with its long-term shift parameter in cell C6. So for this example, you enter the mean and standard deviation as 100 and 0.25 to get a 6 sigma process, and you enter 1.5 as the shift. When you run the simulation, you get the results shown here. Specifically, you get approximately 3.4 defectives per million in cell F16. Any company that can achieve this level of quality is truly first-rate.